My name is Jonathan Cortes, and I will be teaching your workshop today. We have Sergey, who is our moderator. He will be helping out as well as teaching the last portion of the workshop, covering a particular topic known as swarm. And well, yeah, welcome to AEC Tech, or the AEC Tech Masterclasses. So one thing to note is that we do have what's called a breakout room. Breakout rooms are a little function which Sergey has set up. Essentially, if you have a question or anything like that, you can refer to Sergey because he will be the one assisting, and you will be put into a different meeting, let's call it. You'll still be in this workshop, you'll just be in a separate private meeting where you can sort of ask questions, debug, have any sort of anything you need to resolve that you might not want to ask me as I'm like currently teaching or talking, that's okay. Or if you just having problems installing things, feel free to use the breakout rooms or refer to Sergey. And he will gladly help you out and assist you getting anything and everything set up. There's not a lot of plugins, there's not a lot of stuff. It's pretty much just native Grasshopper stuff, native Rhino. Actually, it's only like 2-3 plugins. We're really going to look at the idea of how to manipulate geometry really effectively and how that can tie into parametric workflows and how that can help you create better definitions and share with your team and create better collaboration. Because at the end of the day, it's not just about creating one particular tool, it's more about creating something that you can share with everyone in the projects and so forth, and understanding different ways of tackling different problems. Anyway, without further ado, let's get started. So the agenda of today and the overall of the parametric workflows workshop is going to cover mesh objects. So introduction to mesh objects, we're going to be talking about what they are exactly. You may have heard of them before, you may have played with them before, or you may be an expert on them. Whatever the case, we're going to be talking about them more in detail, how they have existed and changed the way we design and create buildings and other projects in AC. And a couple of the details about them, like what's their topology, why is it important, and why does it matter, and how does that tie into the idea of a parametric workflow. And then lastly, we'll talk about how we can develop workflows that can be shared within different teams, and then how that can tie into the idea of cloud computing, in other words, swarm. Like I said, we'll cover all that shortly. So if you have a chance to go through the Google Drive link, you might have already seen these images, or you might have downloaded and opened those files. That's fine. This is kind of the stuff we'll be tackling at the end. It's kind of 3 kind of typologies that we see a lot in architecture and different kind of problems we're looking at solving, just purely with the idea of decomposing geometry and understanding how to sort of build computational solutions to these projects in a way that we can mix and match them, right? So it's not just like create more massive script that does this entirely. No, the intent is create a series of different tools that you can use for different particular situations. The vaulted pavilion is one, where we're going to discretize it and panelize it with some sort of rationale. The sculpted tower, well, we'll look at the idea of extracting all the, let's call them, attributes of a building from just the geometry itself, specifically like a pseudostructure, panels, and everything, just from the way we manipulate the initial construct, which is that sort of star-looking low-resolution object on the left. And then lastly, we'll look at a generative city block script, which is really looking at the idea of how we can play with geometry in a sense of, I don't want to say clustering, because if you know Grasshopper, it might lead to another idea in your head, but essentially it's the idea of breaking things down into components, into portions. So, you know, we look at a lot, we look at a city, we can think of a region. Within the region, we can think of blocks, and within the blocks, you know, there might be lots, and then the lot has a building, and the building has a particular conditions, and so forth. So all these kind of conceptual steps, starting to look at them, how we can apply them to workflows, and also the way we tackle and script. So before I get started and digging deep, I do want to ask one particular question. Everyone here is, at least not well versed, but somewhat versed in Grasshopper and all that. You can feel free to like say yes into the chat. Because I'd also want to be aware of like some particular subjects I'll be covering and how much detail to go into them. And with the speed of things. That is all. Sweet. Okay, that's awesome. Thank you, everyone. Great. Okay, so it's going to make things a little easier to sort of tackle on, because we'll be talking about more detailed aspects of geometries and how we can sort of manipulate that. So, you know, lists and have all these things are related to the geometry. Okay, awesome. So, as you all may know, in 3D modeling, geometrical objects are typically composed of points, edges, and faces. As we all commonly know, NURBS, which are the primary objects we see in Rhino, are composed of any number of edges, any number of points, any number of faces, as you can see on the diagram on the screen here. Now, the other side of this is meshes, right? Meshes are typically composed of points, edges, and faces as well, but they have a little bit of a limit. They're technically composed of faces that are formed of 3 or 4 edges specifically. Now, Rhino 7 and Rhino 6 actually is supporting what's called n-gons, and n-gons is essentially creating a mesh face that has more than 4 edges, so it's endless amount of edges, right? The practice of using n-gons or not is 100% up to you. There's nothing wrong with it, but for the sake of using the tools that exist today, sort of analysis tools or just like simulation tools and everything, we are still resorting back to the idea of a quad, which is the 4-edge mesh face, and a triangle, which is the 3-edge mesh face. If you've ever seen any like ladybug simulations, weather simulations, or even wind tunnel simulations, oftentimes you see colors depicted back on the object. And those colors are basically reinterpreted across the surface with a series of points that are sampled. You can think of those points as the mesh faces themselves. Each face is one point in a way. But anyway, there's a series of advantages and disadvantages to dealing with faces and so many faces on a given object. I know some people are like, if you use a B-rep, it's so much easier to manage. If you use a mesh, you have so many more points. There's a little bit of benefits to that, and we'll get to that in a second. As you may know, meshes have been used across many different industries for many different things. And of course, popularly, Zaha was also one of the ones to like exploit meshes and really kind of look at the idea of how we can use these geometrical objects to design and create curvilinear objects, organic looking objects. You're not standard designs, right? Not 90 degrees. In the car industry, meshes were really common, and they were really used as a guiding, right? They're essentially used as guide objects that eventually become NURB objects. Because at the end of the day, regardless of the industry, we will have to come back to NURBs to operate, because we need that for fabrication purpose, for accuracy purposes, and so forth. But the intent is, how can we make NURBs and meshes very friendly? How can we have them sort of coexist and work together? So to kind of validate that theory, we have a bunch of different examples of existing projects. So for example, sorry, I have to move something up here. No, apologies. Okay, we have, for example, I'm sorry if I'm butchering names, the Heydar Aliyev Center by Zaha, very well known, but the whole intent here is we're not really looking at the design, we're kind of looking at the sort of topology of the design, the sort of construction of the design. Now, if you think of a mesh and a mesh face and the sort of way it's constructed, it has already informed the way we design and create things in AEC. As you can see here in the structure, you can easily derive this from the way the original mesh object was created, constructed, right? Every single panel was rationalized. The quads, in other words, were looked at as sort of informing factor for construction, for rationalization, for structure.
I just added you to the channel, Mark.
Cool. And then we can also see that in the plans and the sort of close-up shots. We start to see a lot of resemblance of that whole idea of many, many faces existing within a real-world product. Now, that's just one example. There's millions of other examples. We have Coop Himmelb, which is from a long time ago, actually. This is in the early days when we start, not really early days, but when it's actually exploited beyond CAD, beyond the idea of AutoCAD, and start looking at softwares like 3ds Max and all this other stuff to create these kind of tools, to create these kind of constructs. This is more traditional, like triangulated structure, but at the same time, again, it's looking at the sort of mesh construction to extract the way we design, the way we fabricate, the way we construct. So if we start to understand geometry, and we understand also how computers understand geometry, we can really take a better grasp at manipulating whatever we want, the projects that we want, and even create more fluid conversations between, say, architect engineers, or say someone who's doing an analysis and someone who's designing, because of course, like, you know, face count, the number of faces, and how the way the object is constructed in 3D is also reflecting the way the object is constructed in the real world. So all these kind of ideas come together and begin to produce a product that's more unified in the end result, and not sort of brute force, as we've seen in the AEC industry before, and I'm sure everyone has experienced. I have. Now, this is the project I have here. Helios House is kind of like a early adoption of the whole idea of the mesh products, because this is when you just triangulate an object and kind of like keep it as it is, versus the Coop Himmelb one is kind of trying to express something else and using the triangulation as a let's say, what do you call it? Like a design intent. But needless to say, it's still an example of the idea of how we've seen meshes begin to exist within our world today. And then lastly, a smaller scale example, we have sculptures, or sort of architectural sculptures, call them, or engineered sculptures, where meshes are now being used to inform weird ways of creating structure, right? This faceted aluminum sculpture here is obviously driven by a mesh, but if you can still dissect it, you can understand that every little sort of space, you see the rivets and you see the spaces between the rivets, those little circles, or quote unquote circles, are essentially a mesh face. And then you have a triangle connected to the end of the piece. And then you have those little rivets, which arguably can be derived from the edges of the mesh, right? So all these things are basically built on top of themselves. So one object leads to the next, and the next one, and so forth. So it becomes this very fluid way of designing a project, where from design to sort of fabrication, there's a communication in the geometry along the entire way, whether it's meta attributes and information like bin, or whether it's more like obvious, where you're literally extracting a particular aspect of the product or the geometrical object. Again, an example of the mesh translated into real world. And like I said, it's endless. I can keep going on and on about this, but I just wanted to sort of bring awareness about that idea and how we can start to use meshes in a way that can help us design and also help us work with different things. That's not to say we can't use nerves. Of course we can. The whole intent is combining both. It's not being owner of one or the other. It's the whole idea of using both together. And yeah, these are, like I said, many different projects that exist along the world, more faceted versus more organic versus unusual, and somewhere more structural looking, like the crystalline pavilion is like a weird distorted truss thing on 3 tripod truss thing. Anyway, moving on. Okay, so does that make sense to everyone? The idea of a mesh and how it exists in the real world and all this good stuff? Okay, so here we're going to do a little bit of like really simple explanation. Before I even get into this, the idea of what a mesh is, I'm going to just kind of showcase it here, where the idea of a mesh in a very simple sense, like I said, is just an object that is derived of a series of points, edges, and a sort of face representation. So if we were to take this particular object and quote unquote subdivide it, we would get more faces back, right? That's just sort of like adding to the construction of the mesh. If you start to understand how that gets constructed, you really start to understand how to manipulate geometry in many, many different ways. So if you think of a mesh as just a point and then another point, that creates an edge, and that edge already has a particular direction if you imagine vectors. And if you kind of keep that logic going, where point 0 goes to point 1, and then point 1 goes to point 2, you've created 2 vectors or 2 lines with a particular direction, as well as they have some sort of order. So 0, 1 created line 0, 1, 2 created line 1, and that kind of mentality starts to continue. And that's also the way that most computers kind of construct physical meshes, and as you see in your modeling applications, in this case, Rhino. We're looking at that order and how that order can sort of communicate across. Now, if you take that particular concept and apply it on a given object, you can see the order following through. So you have 0, 1, 2, 3 on this one, the mesh face 1, and then that kind of logic goes across, where it goes 0, 1, 2, 3, and it keeps running across. Now, if you take every single object and you sort of repeat it, or you take a single edge and you just add 4 more, you would get something like this. that's called the idea of subdivision. Now, subdivision can do many, many different things, like smoothing and just adding panels or sort of faces per se. But once we get an understanding of how the subdivision is operating and how these things are sort of being built together, we can have a better understanding as to how to manipulate it and how it actually matters and how we can use it for just general construction for projects and designing, etc. Now, the reason why those things I just mentioned are important is because meshes have a weird or interesting thing called topology, which I've already talked about loosely, but the idea of this thing is like, why does it matter, right? Why does this topology matter? Why does the order of these faces matter in any particular way? In this little diagram you see here, you start to get a better sense of how subdivision can start to influence the way a mesh is sort of smooth. And if you think about the idea of a mesh as a control object, right, like a low resolution mesh being the control and the high resolution mesh being the one that's been subdivided and smooth, you can kind of compare that to the idea of editing a curve. If you've ever edited a curve in Rhino, you have control points. Control points move around and do a lot of things, but control points are still kind of a sort of, what do you call it? A polyline representation of a curve. To give an example of that, as I'm sure you've done before, when you draw a curve in Rhino, you have that sort of faceted object that sits around it. It's kind of the same idea of a mesh, right? To recreate a particular smooth object, you need some sort of mathematical interpolation between a series of fixed positions in space. So we have the sort of polyline object, which exists here. And that polyline object can be referred to as the control object. That control object, as we manipulate it, can ultimately manipulate the mesh itself. So, or I guess in this case, the curve itself, right? Now, again, this is pretty much one of the biggest standing logics behind mesh construction. And for the fact of that, just sub-D modeling, which I'm sure you people have heard of, as it's going to come full featured in Rhino 7. And it's kind of a work in progress right now, but we're looking at ways around it. Okay, and then also, oops, sorry. One particular thing that's very, very important for sort of nerve reconstruction from a particular mesh object that's been sculpted is the idea of being able to create regions from these subdivided meshes. So this is how, what we call sort of the discrete track of history, where every mesh gets subdivided, but as it gets subdivided, they have a particular order they're subdividing around, and then that can create sort of patches and regions that we can use to reconstruct surfaces and rational, clean surfaces that we can use for anything really, for any kind of purpose we're looking for, and not just rely on the faceted mesh object. Of course, there's also topology, where we can edit topology and do a lot of funny things. We can directionally divide it. We can add 4 faces within. Any face can have any kind of operation, but when you do that on a holistic, say on a global scale, you start looking at different ways of panelization. You start looking at different ways of seam lines, construction lines, guidelines. You start looking at things that are very informative in the sense of just general designing. And lastly, before we kick off the example files, topology manipulation, as I mentioned earlier, n-gons. If we can understand how a mesh is constructed, sort of a triangulated mesh, we can apply various degrees of algorithms, such as the idea of a hexagonal looking pattern on it, which I'm sure you've seen a lot before, but essentially, you take a center point and then you take the points connections and then you derive the midpoint of each connection and you connect them in a sort of circle fashion, you start to get the diagram in blue. And if we take that and apply it to a holistic object, then we start to get interesting things like the little hexagonal pattern object we see on the screen. Cool. So to continue again, following all those different things I've said, the idea of mesh topology, order, construction of faces, and how all these things can sort of tie together, can ultimately let us design with intention, not just design for the pure idea of sketching and like looking at things sporadically, but also design with a particular end goal and something that can be rationalized more so. So if we think of the way a mesh face is constructed and those edges are constructed, we can start to extract what's called an order from the topology, and then that particular order, which can be referred to as U and V, can begin to show directions, like sort of two-directional topologies that can be playing with together, and then that can also help us build many different kind of design intents, discretize, panelize, and so forth. It's a particular trick that's very simple, but underused in a way. It exists in some projects today, but it's also kind of the idea of instead of brute forcing a couple ideas, then we can look at the geometry and extract much more control over it. For example, Zaha, Hadid International Culture and Arts Center in China, I believe, is kind of an example of that. And then we start to see how the topology gets subdivided in regions where they need it. This could be, I mean, there's millions of reasons why it could be way altered in those particular regions here where we have a higher density versus lower density. But again, that's a fabrication reason where they need more panels for the curvature, they need more panels for other particular conditions. It doesn't matter. The point is, those are being derived back from the geometry as it's being constructed. And then we can also start to see the sort of construction of the overall object be a reflection of the way it was modeled in 3D. And of course, one of the biggest questions is going to be like, how do you control panel sizing? So that way you don't have like a billion unique panels. Well, that's also why we have the ability to use Grasshopper and all these sort of computational solutions, because even though we can design freely, we can also look at the idea of constraining edges. If we understand how the object is constructed, we can take any individual edge and start constraining it in some way where it's a fixed edge length. And then those edge lengths can be then rationalized so that we have some number of repeating panels versus a massive collection of unique panels, which obviously we do not want. Oops, does it go? Okay. So we're going to jump into the example files, but before we get on that, does everybody understand the concept of like meshes and how they can be used effectively with nerves, and at least the way I presented it so far? Do you have any questions about that or anything like that? Anyone at all? All right, well, if no one has any questions, then we can go ahead and start looking at the pavilion example. So the pavilion example is a simplified example of the tower. So now I highly encourage everyone to open the files, take a look at the contents, try to read through it, get a better understanding of it. If you've installed the plugins, that is fantastic, because if it should be an interactive workshop. So if you're just kind of sitting and watching and listening, it won't be quite the same as like you following along and trying to build it and edit and customize things. The way these example files are built are intended to be messed with, for lack of better words. They're intended to be customized, edited, broken. If you can break them and do weird things with it, that is the goal. But again, we're going to walk through these different solutions and conditions and talk about how they can be applied for many different things. We're going to go through the first example file, and depending on how that goes, we may or may not take a break after the first example file and then come back. Something short, like a 5 or 10 minute break. So everyone can go ahead and like open up these two files, the Pavilion Heydar 3DM and the Pavilion Grasshopper files. And if you get some sort of error with some plugin or something missing, please let me know. Please tell me, and we will gladly assist you with that. Also, in this time, if you had the chance to do the swarm or look at swarm, please go ahead and do so, because that is coming on later. And it'd be great if people could have it installed on their computer so they can actually get a chance to use Swarm and understand how effective it can be for what I'm about to discuss now. So anyway, okay. So to start, like I was mentioning earlier, if we look at a mesh as a control object, as we see here, we can start to think about the idea of subdivision. We can start to think about the idea of sculpting, and we can start to think about the idea of how a faceted, rugged object can inform a sort of more organic and more curvilinear object. So in the Grasshopper script, if you have it open and you're able to look at it, you'll see a couple of groups that are named with a series of steps that we're talking about. So in this case, we want to look at we're going to start with a very simple subdivision of the mesh. Now, one thing that I do want to show, for example, is something called a display pipeline, which is built into Grasshopper, which I'm not sure if you guys have had the chance to play with it or whatnot, but it's a fantastic tool for doing live edits on a mesh or any particular object in this case. So, for example, I'm going to take the Pavilion control object, and then that's going to be my layer name here. And then I'm going to toggle the option that says geometry. So as you can see, it's automatically reading back from Rhino the contents of Rhino within that specific layer. And since I toggled on the mesh type filter, it's only returning back a specific filter. If I put a point in this layer, nothing really happens. It won't show up on here, unless of course I enable the points. And if I do, this is going to go red because I can't convert a point to a mesh. This is a fairly useful tool whenever you're doing any sort of live editing or just sketching out your Grasshopper definitions or solutions for a project that you're unaware of. So in this case, I'm going to go ahead and turn this off and turn this off to describe something. Okay, so we're going to have this turned on. And as you can see, with a very simple cat multiplex subdivision from the Mesh Plus plugin, at a level 2, we can start to get an object that's pretty much sculpted, for lack of a better sense, but it's also really easy to edit and work with. As you may know, we can start to manipulate it and do funny things with it. We can have it do strange things and have it sort of move around. Let's say you have a particular site that needs a particular set of conditions. You can start to edit those particular constructs and then have it fine-tuned to that, which is very, very useful. And then also to turn on the edges in Grasshopper, if you don't already know, it is Control M, Control plus M. And if you just do that, you can turn off the edges of your meshes on and off, which is very useful for when you're doing this kind of work. So sculpting away. Now let's say I built this mesh object and I wanted to add a particular face on it. So let's say I do 3D face, which is the Rhino command of adding mesh faces. So we can build a face here like this, and then we can build a face over here like so. And then if we take everything and just join mold, sorry, I forgot to plug that in. We can start to see that it's all interconnecting live. We can keep adding random mesh objects, and then you can watch them basically like subdivide live on the screen. And that's because of the benefit of the pipeline. The geometry pipeline lets you essentially build while it's hooked up to the script and it's operating, doing many, many things. So let's go back in time a little bit. Right. Okay. Okay. So if you have the chance to play with that, I highly recommend doing that. Do not enable the entire script just yet. We're going to walk through this and explain what's happening, what things are happening where. I would enable portions of it as I walk through it and try to rebuild it on your own, sort of copying and pasting things around and changing settings to get a better understanding of what's happening. So in here, all that's really happening is the mesh is getting subdivided many times, and we can go ahead and change this number. And as you've seen, you understand the idea of subdivision, where every time it takes a vertex and moves it, and by vertex I mean any given point connected to a face, it then will find its new location, and based on the new vertices around it, it'll kind of smooth out a little bit. If you want technical explanations, that wasn't really a technical explanation. Please speak up or please say something. I would be more than happy to give a lot of technical answers to things. I'm giving more of a sort of general answer right now to things, but please post a question on the channel or go ahead and speak up through the chat. Again, we can make this a conversation. It does not have to be a single sort of lecture style workshop. And then, yeah, so go ahead and say something if you need. Anyway, moving on. So there's a couple of components that are happening here. In this case, what's happening in the next set is a thickening of the mesh. So as you know, with meshes, you can thicken them, you can do many different things with them, you can manipulate them freely, and computationally speaking, they do not consume memory as much as a nerves object. And the reason why that is because nerves are mathematically driven objects. So they're very, very complex. They're very, very computationally expensive versus meshes are not as much because they're very simple objects. They're points in space that move around, and depending on how the points are connected, you can get various interpretations of objects. In this case, we're just thickening it and extracting the thickened border, which is this particular thing, to basically give the pavilion a little bit of thickness, not just be paper thin. And that's automatically set there, and that's one of our outputs already, so that's all we're looking for. Now, there's a little bit of a divergence here that we're going to look at in a second. So before we dive into the whole concept of directions and whatnot, we are going to dive into the idea of how to reconstruct a clean NURB surface from a particular mesh object. Now, the only caveat to this is that, one second, put this here. The only caveat to this is that the NURBS object needs to derive itself from a clean, and when I say clean, a sort of subdivided mesh, right? Because the way the mesh subdivides gives us a level of control and a level of conditions that we can use to sort of reorient and resort the faces and then build a clean NURBS model that we can use for really anything. If you remember Rhino 5 days, this would have been a blessing because can't make 2D from meshes in Rhino 5. We kind of can if you convert, but nowadays you can make 2D from meshes, but you still get a bunch of faces and a bunch of conditions. In this case, now we have clean surfaces that we can use for whatever reason. If your intent is to sculpt a quick mesh, get a surface, and then work from there, then that's already something you can do. And we can talk about this and how this works in a second, but we can also, in the tower example, we look at how we can combine the sort of NURBS result with the mesh result to create something like floor slabs, and then derive quote-unquote structure, and something we can use to inform a general structure of it. But for those who are curious, or we can talk about the idea of how to generate a mesh object, sorry, a surface object from a complex mesh. Now, if you go in the cluster and just get a look at what's happening here, please feel free to take a look through. And if you're a Grasshopper guru, which I'm sure many people here are, they understand, you'll be able to quickly read how these things are operating. They're not very complex. Essentially what's happening is that we're taking the overall mesh, we're splitting it into individual mesh faces. So 384. And then we're also going to parse them and group them into chunks, right? So in this case, we have a series of collection of mesh faces that have been grouped into groups of 4, right? So now we have a series of 4, 4, 4, 4, 4, and that's derived from the idea of the way we, how to explain this? Every time you subdivide a mesh, it's basically the idea of 4. And here's an example of that. So this is, we take this very simple object and then we do something as simple as this. We do, oops. It's basically to the power of 4, right? 1 equals 4, and if we do it again, then those 4 will get subdivided again, each one 4 times. So in this case, we should have a total of 16 faces. So subdivision, regardless if you do a smoothing or not, let's say we decide not to smooth it and keep everything relatively fixed. Subdivision works in that fashion where it takes one object and then adds 4 more objects on top of its existing boundaries and repeats that recursively for as long as you want, really. Keep adding levels to it and complexity. But if we take that idea and reverse engineer it, we can start to sort of group our meshes based on the level of subdivision. So if, going back to the cluster, if we take a given, if we take the mesh, where are you? If we take the mesh and then we simply group it into groups of 4, we have a bunch of chunks here, which are mesh faces that were joined, and then if we bake those out, we start to see these chunks that are representing basically the original meshes before they got subdivided. And then we can take that logic and essentially output it. So we have the mesh groups, the mesh borders, which are we're going to use these to reconstruct the surfaces. We have any inner edges for no particular reason, and the grouping number, right, 4. And now the actual mesh construction, or the surface construction, we're going to take, again, those mesh groups with their borders and the number that we used. And essentially, we are going to take count of their control points. And their control points are going to be used to rebuild a sort of interpolated curve, which is essentially a representation of the smooth mesh in this case. But if you think about a mesh is a representation of the mirror's object, so we're kind of like going back to what it's supposed to be looking like. And then we can use the edge surface to connect the 4 different edges that have been reconstructed. So if I do a branch here, oh, wrong one. And we extract one particular branch. Which one is it? We have this one. Let me copy this over. We can take those 4 edges and reconstruct one surface from it, right? So that particular surface there. And then we can see that mentality applying across to the overall. Now, it's a little bit of a basically mathematical situation where you're taking a count and then checking its relationship to 4, and then grouping along that condition and so forth, and then recreating based on those groups the information to recreate a surface. And as long as you understand that, then eventually you can create the surface that you can use for, again, whatever your purposes are. It's a very useful tool. Now keep in mind that this particular method of resurfacing from a mesh has to derive from a subdivided clean mesh object. You can't just sort of plug in any random mesh into it and expect it to do a mesh to nerve kind of conversion. That's why it's such a complicated task today that so many people in this world are trying to find solutions for it. There's a plugin that exists that still tries to do a lot of solutions for it. But this is, again, one way of sort of solving that problem, as long as you have an initial clean mesh structure to begin with. Now, with that said, we can then look at the actual idea of mesh directional. So you'll see there's a couple of Python components throughout the entire set of scripts that were developed for the idea of explaining the concept of directions and how we can use these effectively. And we're going to build a little grasshopper example talking about how we can replicate the Python code here. Also, if you have any questions regarding the code, regarding Python in general, and how we can use these things to hack, please ask me. Everything here is written by me, so I'll be more than happy to ask how you can integrate this kind of mindset into anything. Or if you know it yourself, which you might. Please feel free to give some feedback if you want. So going back to the example I had earlier on the slides, essentially what's happening here is that we're taking a series of boundaries, face boundaries like so, and then we're then exploding them and then getting the midpoint of every single mesh face, right? Assuming the mesh has a particular order, the way it's constructed has a correct order, we should be able to get some sort of directional lines, such as these, derived from the mesh object. So, face boundaries with that, and then we can evaluate the curve, just as so. And like I said, we want the midpoint, so we do a parameter 0.5, because it refers to the very center of the curve. Once we have that, turn some things off so we can see what's going on. Once we see that, we can start to already kind of derive a sort of connective directionality from this. In this case, we have 4, 4, 4, 4, 4, because we're all dealing with quads. We can do a simple list item, and then we list all 4 items. And then we can just draw lines between them. If the order exists, we shouldn't have to worry about much. As you can see here, the mesh is ordered, so it does have some sort of rationale behind it, and we can start to derive what's called 2 different directions. Right? We can have direction A and direction B, and these can be used for, well, again, any particular purposes. If you think about this as a sort of modeling tool, you can kind of step away from the concept of continuing mesh, and you can use this to loft together if you so please, right? You can create some sort of surfaces that way. You can rebuild those curves and create another thing, of course. You can do a network surface using these two curves, but I'm not sure. But anyway, so again, keeping the whole concept in mind of building up scripts that are sort of like clustered in functions per se, and the different, similar to coding, that we can sort of output different things that we can use for different purposes and not have everything linked back to one particular object that's, if you change it, it crashes everything. So let's go back to this. So that's the concept of mesh directionals. Now, if you have a mesh that's not ordered, which can happen, thankfully, one thing that will solve this is called mesh direction. Mesh direction will take a particular mesh object and basically try to order all the faces. If you think of the order being a sort of the points, try to order them so they're all going a certain direction, I think clockwise, for example. So they're all going 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, and so forth. If this component here by Dalian Piker will do a lot of that work for you, there is a chance that it'll always work, but there's a chance you won't get 100% directionals. That's purely based on the way the mesh is constructed, and it ties back to the idea of clean modeling, right? If your mesh is very clean and very well modeled, then you should be able to always get consistent, clean directionals no matter what. So that's what this Python component is doing. It's giving us basically those directionals back. Now we can use those directionals to build things, right? We can build what I like to call sort of bands, directional bands, or sort of stripes, right? These things are essentially extracted in a very simple way where you just take the polyline and project it back on the mesh, and you find every line's is you take every line, right, on the polyline, every segment, and then get the center point, which is this right here, and then project it back on the mesh and figure out what mesh face that is and put it back. In a demonstration of that, which we can do, going back to the little code we had here, can be done like so. And that's again because this is also a Python script, which is doing the following. So let's say we want this particular direction, or we can take the other one, just for examples. We're going to flatten this list because we want to join all those curves in space, which we already did. And then, like I was saying earlier, project them back. Curve. Curve. And once we project them back on the mesh, then we immediately get an index, mesh closest point. And then we can use that index to reconstruct these sort of stripes per se, right? Or these sort of conditions. We explode them, and we just use list item, like so. And then we join that. And this result should be a total of 24 meshes, which should be the same as the amount of curves we have, 24 polylines. And to just verify that, we're going to bake that out, and there you go. That's the sort of mentality behind, or sort of extracting these sort of topological bands, right? These sort of topological conditions that exist within the mesh. And then, of course, you can just flip it. Once you have the script written, you can literally just flip this and extract your other direction. It's a simple sort of methodology that exists behind meshes, but it's also something very useful. It can be used for, again, any particular purposes. So let's go ahead and get rid of all this. And continue on. So now, once that idea is set in, we can pretty much just use that for whatever we want, right? We can use those sort of directional conditions to penalize or discretize or etc. As the mesh is already kind of discretized inherently, we can look at the idea of how we can use that effectively. So what's happening here, let me turn this on, is that we're taking the individual bands and then we're creating a gap between them. And the way the gap works is basically taking the edges, taking the edges, so imagine point A to point B, and then it's going towards its center. It's going some specified distance. In this case, I'm giving it 1 inch, 1 inch of distance, but you know, if we wanted to give it more, we could. We give it something like 3 inches, and it'll start to work like that. Now, of course, if you go too far, you will get a flip of objects. The good thing about meshes is if they get weird and funky, they do not crash your computer, as if you may know. Where nerves get really funky, if they're not built correctly, you can expect your random to crash, which is an unfortunate situation. But in this case, meshes are not afraid to sort of get really strange. But of course, that's not something you want. You want to be able to control it, so that way your end result is very rational. So once I do the spacing here, the reason why we're going to subdivide each individual one, because we're going to do something that's called pleating. And this particular example can be seen in, where's this project? No, where is it? For example, if we go back to up here. So if we imagine this particular project, we look at the top of it, and it has what I like to call pleating. Pleating is essentially the idea of taking a topological band, subdividing it, and then taking that center line in subdivision and just moving it up in some direction by its normal, right? Or by a z, or it doesn't matter, by some condition. And that's exactly what's happening here. We're taking that sort of center line that's running through, and we are just lifting up what's called the non-naked vertices. So naked being any vertex that's exposed to the edge, non-naked being any vertex that's sitting inside the mesh, that has no sort of exterior exposure. So let's go ahead and see what that looks like. Here we see the mesh is completed, and if you want to see a quick comparison of what that looks like before and after, we can just visualize the mesh before and the mesh after. It kind of looks like a little triangle essentially. And this is also another way of creating thickness to your bands or topological bands if you want. But for the sake of the presentation here, we're going to look at this as sort of just creating a sort of pleating effect. And you can imagine this being sort of shingles, or another way of panelization, another way of creating some sort of, for structural engineers out there, they might see this sort of benefit, creating some sort of strength because the way the object is bending. Stiffness, for lack of better words. And once we do this, we're going to do one more directional derives. We're going to derive the directional one more time in the sort of short direction for the sake of creating panelization. We're going to create panels from that. And again, this is repeating the same example I just showed earlier. Like if you want to build it just purely in Grasshopper, no Python, it's, oops, what is it? Big, there you go. That's all it is. It's again, looking at the meshes, looking at the topological conditions, and deriving a series of conditions from it. So in this case, we derive a series of, you can call these shingles, you can call these discretized bent panels or whatever, and then use that to essentially start discretizing and panelizing the overall structure. So nothing new essentially, still kind of replicating the same thing we built earlier. So let's put this on. So, and again, going back to the idea of using a parametric workflow is that you build definitions or you build things in certain ways that can be applied and shared in different ways. So at this point, we're using the gap again to create some sort of distance between the panels. This could be a fabrication reason. This could be an aesthetic reason. It doesn't matter. But the point is, like, you're getting that control and that fixed control. And of course, if it's built correctly, you can then verify that those distances are exactly 1 inch, if not close, which we can do. So it's moving 1 inch in both directions, therefore creating a 2 inch gap. And if we visualize the earlier mesh, we can start to see that 1 inch is moving this way and 1 inch is moving that way. So these kind of microcontrols are, again, just looking at the edge of the mesh and looking at the way the edge is moving, or the direction of it, and then moving in set direction. So if you think of the mesh and you think of the vertices, you can take this and then scale 1D. It's moving that way, or so to speak. And then that's, once we get to this part, it's essentially the end of the pavilion. The bottom portion here is just purely a coloring idea, mechanism where we're going to take every single panel and color it by area. And if you're familiar with Grasshopper mapping, I'm sure you're familiar with this particular sort of workflow down here. It's used pretty much endlessly across many things, not just for colors, but for anything. And then on top, it's what's called rivets, or as you may know, some sort of connections between two particular things. Now, what's interesting about these rivets is that they're not derived arbitrarily per se, but they're derived from the mesh themselves, where we look at the mesh's edges, right, or the vertex is constructed with, and then we move them inwards. Now, a more sophisticated way to build this would be not just moving towards the center, point B and point A. A more sophisticated way to build this is like if you move it a specific distance, like I'm trying to move everything 4 inches in, but then you can start to think about the idea of maybe one of them has to move 6 inches in for any particular reason, or maybe because it's too close to the stiff edge. So you don't want any particular conflict when you're riveting pieces together or connecting pieces together. It doesn't matter, but the idea is like you have that open to you where you can clearly customize and look at how you can insert exceptions into pre-existing display, respective display. There's into the pre-existing conditions here. So again, it goes back to the idea of deriving information from the object and letting that information be manipulated for your purposes, whether it's for structural purposes or aesthetic purposes or any kind of purposes, doesn't matter. And then we have a mesh sphere just to give it a look and be able to see what it looks like. And the underside of this thing, I left it as the mesh object, or it's not a mesh object, the surface object to be able to sort of understand the differences between the sort of operated mesh on top and the operated reconstructed surface on the bottom. And if that makes sense to you, you can also increase the level so you can get sort of less surface panels to work with. So these are one large swath, another large swath, and so forth. And another thing to note is like once you have these particular workflows set up, you can technically just apply it to other objects. So if we take a given mesh face like this, and then we'll just do something like this. Take a minute to calculate everything, and then let's share. Give it a minute. Ooh, that's a lot of conditions there. Yeah. So it takes a minute to calculate everything, but essentially there's way too many mesh faces going on here because I inserted a very high resolution mesh. But the idea is you have, it's easier. Two. Something simpler like this will be a little safer. There you go. So if you think about this as sort of like a roof or a sort of facade, you can start to imagine the idea of how it can operate in different ways and how you can begin to see responses from it, right? Or even just a very simple inflated shell. Again, the intent is kind of up to you, whatever it wants to be, but once you create it sort of something that works this way, then you can start to begin to create and customize different things and seeing your response live, which is very, 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 very effective for many, many things. It doesn't have to be one specific kind of object. That's kind of the beauty of meshes where they're all constructed the same, so you can technically apply one solution to the others. Not always, but most of the time. Okay. Does anyone have any questions about any of that or all of that or anything like that? I just hit 10, so I was going to transfer over to the towers file. Towers file is a little bit in depth, so it covers everything we just covered plus a lot more. So I was wondering to see if anyone had any questions or anything like that, anything you'd like to talk about right now, for like the next 5 to 10 minutes. If not, I encourage everyone to take just a mini break so we can, before we look at the tower. Yeah, if you have anything, feel free to unmute yourself and talk or post the question on the Slack channel. And also, if you haven't done so already, this would be a good time to take a look at Swarm. And maybe if you're trying to get an account and get Swarm up and running, feel free to ask Sergey or myself. Either one is perfectly fine. Yeah. Feel free to take a 5-minute break. So, hi everyone. Welcome back. If you, I don't know if you took a break or not, or got coffee, or depending on what time zone it is, just got water, anything. Yeah, if you're ready, you can go ahead and move over to the tower and talk about that, and talk about those particular workflows and the idea behind it. Of course, if you have any questions about the pavilion or anything that we talked about in the pavilion and how any of that stuff works, yeah, feel free to post it now so we can have, like, we can talk about it now and get up and running about it. The tower is a little bit more, like I said, in depth, and it's like looking at the idea of extracting a lot of different things. Extracting, floor slabs and extracting pseudo framing. This is pseudo framing. I'm going to be very explicit about that. I'm not an engineer. Also extracting, what could be considered as like the main structure and how that can be derived from geometry and everything, and how all these things can play with each other once more. And it's all kind of speculative, but it's the idea of how you can take a project from an SD phase to DD phase with a little bit more information, and not just kind of brute forcing things all around, right? And then also being able to have some sort of control over an object that is unusual per se, and how that can be connected into more fluid discussions with people who don't, with anyone who doesn't understand geometry as well or understand computational solutions as well. Anyway, so yeah, if you have any questions before we get started, please ask. Also, I think Shannon might have mentioned this before. I'm not sure if you guys saw it, but in the Slack channel, we have what's called the workshop show-off, which is going to be running throughout the entire set of workshops. And the whole point of that is to get everyone to whatever they learn from all the workshops you end up taking, to just post it on there. Like if it's a workshop that's using Core Studio tools, which there is one, post whatever cool stuff you made from there, or anything you make from here. Like if you happen to mess with these scripts and create something very different, or like mess with the parameters and completely alter the solutions, post that on there. Or if you go to, like, I don't know, there's many workshops. The point is, feel free to post the stuff you do on there, and we have sort of like an open forum of everything, the things that everything's learning and being able to use. So that would be really exciting. Also, in our particular channel, the Parametric Workflows channel, you can also post there, which is kind of redundant, but yeah, feel free to add stuff. Anyway, so let's talk about the tower, the workflows and the ideas behind the tower, and how this thing got constructed, and how you can take some of these particular concepts and apply them on your end. So for the tower, do you have any more? For the tower, this is the control object. And again, if we talk about meshes as being sort of control objects or smoother objects, this is basically the idea of taking one facade or one portion of the facade and then arraying it around, and then also mirroring it vertically or horizontally, I should say, to get the overall extent. Now, this uses a handful of different grasshopper operations and geometrical operations to get that aesthetic, but let's take a look at it. So, like I was saying at first, we have the control object, and then we have what's called a control curve, or what I call a control curve. Now, these two are necessary because there is a polygon that exists that exists in the file, and this particular polygon is what we're going to use to sort of create the initial facets of the tower. Now, the tower can be much simpler. It doesn't have to be this funky looking object. If anything, you can make it as simple as you want by creating a vertical extrusion, like a rectangle. I just added a couple faces to it because just wanted to sculpt and mess around with it and see what I could do once I tie it into all the rest of the functions. But so anyway, so there's a polygon and there's a series of lines here. Now the line is going to inform me where this thing will sit in the polygon, and then the mesh will then be oriented back onto there. So by taking a polygon and exploding into a number of segments, into individual segments, and then taking the mesh itself, along with the center point of the line and the center point of the polygons, we can use what's called orient direction. Now, orient direction requires point direction, point direction, point A, point B, point, and so forth. And then geometry to orient. So you're going to take the very first point and its direction, which is this object here. It's going, sorry, the arrow is going that way. And then it's going to just basically literally do something like this and map it back. Pretty simple, but pretty useful when you're doing all sorts of operations. And once you map it back, you get something like this, which is it's useful and it's good to use. But if you notice, there's a little bit of discrepancy between the edges because maybe for some reason this line isn't exactly the same length as the line on the polygon. But that's when we can just compare the lines themselves, right? We compare the length of this one versus the length of the individual polygons. And once we do a comparison division, we can get back what's called a sort of percentage difference, right? So arguably, we need to scale this particular control object by 1.08, whatever numbers. So we scale it by that factor, and we are able to control the object a little more so we can get that going. And then there's a C scale, which is independently tied, which I'm just using it to sort of bump it up a little bit, make it a little taller. But once that's set up, if I just disconnect this for a second, I'll turn this on. We have that. And then we also, again, going back to the initial example, we can really just mess with this as much as we want, of course, within reason. Arguably, you could leave your project at here and just play with that and see what you can do. You can take that and apply it to the other script we were talking about, the Pavilion, and see where that goes. But it's, again, taking the idea of your workflows are parametric in a meta sense, where they can both be intertwined and going back and forth. And it's not just creating one solution for one object, one case, one thing. It's the idea of being able to create sort of clusters of different solutions and then have them sort of have an input outputs and have them communicate back and forth. So anyway, I'm gonna turn this to step. So I'm gonna go to the second portion of this. In the second portion, it does sort of the rest of the tower, right? So all it's really doing is that you're taking a particular mesh and then you're taking the bounding box of it so that way we can get a plane. And then the plane is, you cannot see that plane, there it is. Let me change that to speed plane size. 50. Okay, there you go. So why is this plane important? Why does this matter? Why are we getting the top plane of the bounding box? Because we're using that to mirror. If you ever play with mirror command in Rhino, you know you need some sort of mirror axis. In this case, we're going to be using that as a mirror axis, as the plane to mirror. And then, well, that's it. We can just mirror it up. And then we'll do a scaling. In this case, I'm going to do a z-scale, but using the plane as a sort of axis to scale from. So if it was in the center, this thing would sort of scale globally. But since it's not in the center, it's at the very bottom, it's going to scale from the bottom upwards to whatever particular scale I set it to. So I wanted to do twice its height, and it's twice the height now. So that's the sort of simple setup for the tower, right? This is essentially what could be controlled or considered as another control object. You know, technically speaking, you can bake this out and edit it once more and start to create sort of a series of, you know, call them custom exceptions in the overall product before you take it further down the pipeline of the overall system. And again, it's the idea of being able to take geometry out, edit it, and put it back in, understanding how it's operating. So here we're going to turn this off and turn the next session on. Oops. Okay, so all it's doing here, which is, to be honest, not much, it's basically subdividing the object. As we can see, we're taking a particular object, and there's these things called weights, which you may be familiar with. There's a face distance, there's a edge weight, and then there's also a vertex weight. The reason why I put all three 0 is because I want to subdivide the object, but I don't want it to smooth. I just want it to basically add more panels to it. So if we just zoom in down here, and then we look at this, it's just taking the same thing and adding more panels to it. Right, we're just subdividing. So I will display. There you go, that's easier. We're adding more faces, more edges to it. That's all we're doing, but we don't want it to smooth. We want it to still keep its sort of rigid look, because then we'll be doing some smoothing later. That's also a benefit of subdivision. You can control whether or not it's smooth. And if you want to get really picky with the way you subdivide, you can add a series of lists to this that every vertex has a certain amount of distance it can move once it smooths, or you can create a crease. A crease is otherwise known as sort of a fixed edge, and then the rest of it starts to smooth, and that can be controlled by the distance in relation to the vertex. So 19 vertices, so we would need 19 distances or weights. In this case, we're going to take it as it is. And then once we have our new control object, the subdivided object, we have a bunch of options here that essentially can let you rotate the object. Mine is by default set to 0, but it's another transformation tool that you can sort of alter the overall and, again, do some strange things to it. But it's for the purpose of looking at the freedom of geometry with meshes. Like, you can start to take a mesh that has many faces and start to affect it and rotate it and still use it for other things down the line, and not have to worry about like terrible consequences of like crashing your Rhino and all that good stuff. Or actually not good stuff. And the way that's operating is we're basically taking a bounding box, taking a sort of the center axis of the entire tower, and then we're shrinking it down to a certain region, as you can see, because the way we shrink it can let us alter only a portion of the structure of the overall, right? If I were to change this to be, 0 to 1, it's basically going to just twist the entire thing. If I change this more so, you start to see the effect kind of traveling across the overall. Or we can sort of fine tune it to a very specific location, right at the center, right? If we do something like 0.2366. For now, I'm not going to rotate it. I'm just going to leave it as it is to keep going with the exercise. Go ahead and cancel this and this. So going back to the idea of edge weights and whatnot, here what we're doing is subdivisions. So these subdivisions are now actually smoothing. So if you notice, there's a sort of smooth condition to it versus the previous object is very faceted. Now it got subdivided and got smooth because aesthetic choices, but also because I'm looking after more faces, trying to get more series of panels and trying to discover how many panels I can get from the initial mesh topology. And arguably speaking, you could take this particular object here and then say you measure this out and this happens to be way too long for some fabrication reason. You can take these couple edges or these couple faces and or sort of topological band and then look at subdividing that in one specific direction. Or if you really want to get very exact, which tends to happen, obviously when we get to fabrication level, we can look at the idea of creating a specific distance. So let's say this only moves down, let's make it 40. So that's 40 inches down, and then this will also be 40 inches down. 40. And then we could technically, with this logic in place, we could search every single top edge of that sort of topological band and add a sort of new set of faces that are only distanced by 40 inches. And it could sort of travel around, and then we could also just kind of keep that logic going, right? 40 consistent, 40 consistent, 40 consistent. Again, it's going back to the idea of being able to manipulate these objects effectively and just being able to edit freely. So let's go back to this. Okay, so here there's a bunch of stuff that's happening. If you looked at the script, it kind of splits into many different things because we start to look at nerves and mesh cooperation together. So let's talk about that for a second. So here what's happening is more of a design choice, but I'm basically isolating a portion of the overall to become, let's say that's the sort of glazing area where you get the most glazing, versus the rest are just standard panels, like aluminum panels or something. And that's what I'm doing here. And the way that's operating is I'm basically taking directionals, as you can see here, and then extracting a series of topological bands here. And then with those topological bands, I'm basically identifying which ones are closed, which ones are open. So if we look at the bottom, if curves that are periodic or closed would be essentially something similar to like a circle or an ellipse or something, versus curves that are not closed or not periodic will be something like this. They're kind of open. They can be very close to being closed, but they won't be. So by that logic, I'm easily identifying the sort of center portion as that's the closed curve, and then isolating that, and then isolating the rest of it to be operations for something else. Now, before we go deeper into those operations, let's go back and see what's happening at the bottom. Turn this off and turn this off. Okay. So here, nothing different from the previous file where we were looking at just thickening and how thickening can give us things. But in this case, we're just looking at offsetting. We're going to take the object and just offset it some particular dimension back. Offsetting with meshes and nerves offsets are very different because the way you offset a mesh is essentially just moving a bunch of vertices or points in space along its normal, a particular distance. You can get mathematically accurate with it by calculating its normal in relationship to its angle to its connecting neighbors. Basically, like take this point and I check that point, that point, that point, that point, and I check those normals and I see the angles, and that can inform me. It's a little bit of trick, and that can inform me a more accurate offset. Alternatively, offsetting surfaces or mesh or B-reps, which I'm sure everyone has tried, can get really messy really quickly because that's again a much more complicated mathematical equation. And yeah. So once we offset that, we can continue on and do our little mesh to surface conversion. And we've created this clean surface here from the mesh that we sculpted. And these are clean surface panels we can use for, again, any given purposes or just for whatever reason. And again, that ties back to the level of surface paneling or reconstruction. We can change that number down to 1, right? And then you get many, many, many more panels. Or we can keep it higher. Pretty sure I can get to 3. Nope, sorry, can't go to 3. If you have a question about that, I'll answer it, but I'm going to continue with this first. And then there's our surface. The reason why these surfaces are very useful and necessary now is because towards the bottom of the script here, we're going to do something that everybody knows whenever you're designing a tower or taking a mass and splitting it, right? Essentially what's happening is we're taking set surfaces and then we're taking the sort of center line of the overall object, creating a bunch of planes that run through it. And then the way these planes are operating are also based on a particular distance threshold. So I'm evaluating the curve within 0 and 1, the parameters, and then try and identify a sort of new set to fit within. And then that's going to give me a set of frames to create floor slabs from. In this case, I'm doing 10, I'm converting it to 120. So there's about 12 feet between each individual point. And then I put a plane and we just do a simple intersection. The reason why this is much more better to do with nerves versus meshes is because if we were to intersect the mesh, we wouldn't get a clean curve per se. We would get a very faceted object. This is has many, many points, as you may know, but we would get something like that control object here. Now, when you're dealing with situations like this, like floor plates and slabs and sculpted conditions, you don't necessarily want a faceted object because it can get very complicated very quickly and also unnecessary. So once we have our flow steps in, we're gonna have to jump back. Yeah, that's okay. We're gonna disable this for a second. And all we're doing here is basically setting up the slabs and the core. So we're using the planes and the existing slabs to then basically create a set of cores, right, to fit within. So we can have like an elevator core running through the very center of the overall building, and then that can lead to all those particular floors. But what's happening here, that there's a bunch of like weird components doing many things, is that I personally wanted to reconstruct these curves so that way they're a little cleaner, because as you know, when you do any sort of contours, things get really complicated really quickly and messy. So what's happening is I'm taking the curves and then I'm picking one particular endpoint, in this case, the very bottom endpoint. And then that endpoint is going to get projected all vertically through. And then that's going to be my curve seam. Now, the reason why a curve seam is important is because when you're subdividing a curve, it needs somewhere to start the subdivision as it travels around the curve. Versus if I were to just subdivide the initial curves without the seam, you would get sort of inconsistent relationships everywhere. Like the points would not align, for lack of better words. By doing this operations, I can align the points very effectively and have that sort of consistent rhythm all around. The amount of points that you pick is up to you, of course. You don't have to have 100. I only picked 100 because I wanted to have some sort of accurate representation of the original curve object. And then I rebuild it, as you can see here. And then with that rebuilt object, I can then do an offset inwards to give a little spacing between the facade and the actual edge of slab. And we just tie that into the floor cores, which, to explain that, is basically taking the planes and then making a rectangle as the rectangles sit on every single plane. You give it some dimension. I give it 120 inches, which is 12 feet. Technically 12 feet divided by 2. It's 24 feet all across. And I just built my new slabs. So if we take a second to see what that looks like, we just turn these on. The rest of this off. And here we're already starting to see something, right? Something that we can eventually use to reason and rationalize with once we start to look at more detailed design discussions, not just sort of sketch design discussions. And then lastly, we're going to basically create surfaces from the floor slabs. And as you may know, we can just combine, as long as the order of the data is matching correctly, as it should, we can just combine them together and then create a series of boundary surfaces with an exception in the center as we wanted for the core. And then that can be our flow slabs. Of course, you can do whatever you want with that. You can thicken them, you can make them have more holes in it, or etc. That's up to you. If anything, I highly welcome people to break stuff up and like keep adding to this, as the way this is built is currently with input-output mentality. So, you know, you can take a set of surfaces and you know, maybe introduce spacing for stairs, introduce spacing for other structural elements, such as like vertical columns that are running through. There's a pseudo framing happening here, which is again very much sketch. It is by no means an accurate representation of framing, but it's looking at the idea that, you know, we can have a relationship between the core and the edge of the slab purely just by looking at the points and how they can sort of talk to each other, and eventually creating something like this, which can use to inform an early sketch of framing or something like that. So now jumping back to the rest of the project, since we have sort of the interior up and running, now we need to do the overall, as in the exterior of the facade. So as you remember before, there was a little bit of split between the top and the bottom, top and bottom here. Now, what happens here, just get this to explain, is that the top and the bottom both get subdivided and they have a different treatment. So the middle gets subdivided and it remains relatively flat with the edge weights of 0, 0, 0. So in other words, we're just adding more panels, right? panels proportionally. And in the other one, we're subdividing it, but we're not sort of just merely adding more panels. We're actually smoothing it to some degree. So that way we're sort of smoothing out any kinks or anything like that around it, except any edge of it, so any sort of edge conditions must stay locked in place. And then once we have those two, we are going ahead and complete them for aesthetic reasons in this case, to get some sort of look to it. And again, if you remember pleating from before, it's going to take the very center of the object and just push it up along the normal of the object. And of course, you can exaggerate that and give it some more conditions. And if you're curious about what the false does, I can explain that here. But essentially, the false will just reverse the effect. So it'll pleat in the opposing direction, essentially not using the centers. It'll take the exposed edges and move them outwards instead of using the center edge and moving outwards. Just a little tool there. Okay, so then here, what's happening is that we're doing similar operations before. We're getting all our little panels out, and then we're purely just getting some sort of bands that we can then use to do some more paneling. This is a very similar operation to the pavilion, as you can see. We're doing another sort of shingle-looking aesthetic, and we're taking out those individual panels and doing something with them, or collecting them in this case. And if you're familiar with groups, groups are very useful. It's essentially the idea of a tree, but it's not a tree. It's just a flat list of objects that, it's just another way of a tree, but it tends to be useful in certain operations because you don't have to exit the idea of a flat list. Now, we can cover that more so later on, or if you have questions, please ask away. And we can talk about how useful it is to use a group versus a tree. But anyway, there's another operation. Okay, so we got the facade set up, and then before we continue on the facade, we're going to look at the surface again, and we're going to look at how the surface can begin to inform some sort of structural information, right? Some sort of structural discussion, right? So if we look at the facade and we start looking at all these splits along the surface, along the original way we constructed it, we can imagine, we can think about how this can inform the way we construct things, right? General construction, or even some sort of discussion that could talk to an engineer and be like, hey, there's a structural idea, is this feasible, is this not, or is this something that we can use to strengthen and so forth, by getting these sort of edges of the panels. So over here. And then all this is doing here is basically isolating the vertical edges from the overall, or trying to get the vertical edges from the overall. And how that's operating is essentially, okay. As you can see, most edges that are facing up have been extracted versus any edges that are considered horizontal have not been extracted. And the way that's operating is purely based on the directional of the direction of the curve, right? So if we do something as simple as display a vector, we can start to understand what that is. Right, so we start to see here there's a couple of directions going on, but all we're really looking at is any particular direction that's almost horizontal. And the way we determine that is that we compare it to the z of the world. So in other words, if you imagine the center of the C-plane of Rhino, and take that particular z there and then compare it back and forth, anything that's considered, say, 90 degrees or similar, is considered horizontal. Anything that's not will then be considered a vertical number, at least for this particular example. So once we have that, we can move forward and remove any numbers that we consider horizontal. And then we have somewhat of something that we could use to have a structural idea with. Okay. So now we're going to turn on a couple of different elements here. Turn this on. Turn this on. So now this here is, So in the section that's called middle extract window panels, we're going to take the middle portion along with these derived curves, and all we're doing is that we're just getting sort of an attractor. In other words, whichever given panel is closest to the curve will be kept. Whatever panel is furthest away will be removed for another purposes. And we're going to give it some sort of distance threshold. We're checking the distance again between point and curve, and if you're smaller than some distance, in this case 50, then you're going to be kept. And if you're not, then you're going to be just parsed out. So in this case, these are going to be the sort of glazing panels, or the panels that get the most amount of glazing. And then once we've isolated those two conditions, we can easily start to extract different properties from it. So this is just a quick way of creating framing. There's a particular component called frame plus 0, and it's in the mesh plus component library that David Mans wrote. And essentially all this is doing is creating a frame around inside the face, and then within the face it's creating another face. It's a simple little script that does a lot of good work. But for our purposes here, for the sake of just creating the overall, you can create the framing of the windows, sort of the mullion or so to speak. And then we can create the actual glazing elements, which are any particular framing object inside that. And then the way this is operating is that we're going to give a sort of, evaluates a distance here, where it says evaluates a new vertex between inputs and face center, and that's the percentage. So everything's being moved sort of 20% inwards, 0.2. Inwards to the face versus, and then lastly we have this condition here where it says close. Close is what creates the actual interior face. If you toggle that to false, you're basically not going to have an interior face. It's just going to be empty. And then we do a little bit of mesh explode, and since we understand the interior face is always going to be the last member of the list of that mesh, we can isolate them by just extracting the very last index item. By taking the list length and doing a -1 on it, and we have something like this. And then we group them because we want to sort of keep them together to some degree, and get rid of trees for now. So, and now jumping back to the structure before we end up getting into the actual panelization. Up until now, we probably have something like this. We've identified the glazing elements, and we identified the other panels, but we haven't been able to reconstruct or paint anything else. So the curve that we were originally looking at, which is this object here, there's a little bit of a split that goes down, and this split talks about taking, not re-rationalizing, but subdividing that particular curve into a series of equalized segments that can be used for, let's say for engineering platforms that need a series of segments with a certain distance between them, or also for visualization purposes. So in this case, if I were to turn off the surface, we start to see something like that could be called, again, a principal structure, the main structure, right? In this case, we're seeing the series of conditions get thickened, and yeah. And it's very simple. It's taking the segments, exploding them, and then checking the length, dividing them by desired length, so 120, and then whatever count that gives back. So in this case, what is a breakout room? So 1 second. So, hold on, there's a little bit of a bug with Thing Central, my bad. Okay, moving on. So, yeah, so once we get that particular division, we can then round it up to get a desired sort of fixed edge length. So they're all trying to be 120 each. And then we just use that to divide the curves. And then once we divide them, we can reconstruct it with a polyline. In this case, this can be used, again, for many purposes, such as analytical purposes or just visualization purposes. And then in this case, there's a particular component. Let me know if this doesn't show up on anyone's computers. If it doesn't, I'll get that. I can get that fixed for you really quickly. But essentially, we use this to basically create a mesh representation of the structure. Something we can just use for aesthetic purposes and get a look. And yeah, that's it. And then we combine it and smooth it out, so we can get something like what you see on the screen here. Now, all that's really missing is the sort of latter part of it, which is just kind of, for lack of better words, the coloring. So essentially what happens is we take all the panels, we combine them, and we have just a series of collections here. So if I were to take a branch and see what that looks like. Let's say paper and branch. It's basically recombining them back in the topological bands and then just coloring them based on their area. So in this case, to save computation time, I did a false area. So what that is I took the bounding box of every individual panel, which is a very, very fast way to compute instead of actually calculating mathematical areas. And then once I get that bounding box, I get the area of the bounding box, and then I use that to derive the color scheme, as you can see here. And of course, like that can be anything. It doesn't have to be the color scheme I provided on here. You can have something like this and get sort of a false color analysis, or get something more stylistic or more rainbowy. It doesn't matter, right? It's anything that you're looking for, but it's looking at the attributes of an object and then coloring based on those attributes, and that can be infinite how you decide to color that. And yeah, that's kind of the gist of the overall of the tower. Does anyone have any questions regarding like any of these steps, whether it's like the very initial one, such as the polygon, or sort of something later on in regards to parsing or groups or anything like that? Does anyone have any questions regarding any of that? If you do, please post it somewhere on the chat, or post it on the Slack channel, anywhere really. Because then we're gonna talk about MetaHopper for a second. We're gonna take a little bit of split and talk about why this is very useful for the workflows that you create. But yeah, before we do that, I just want to kind of give it a moment for break and see if anyone has anything of interest to talk about.
Actually, I have a quick question. So from the standpoint of going from, this kind of sophisticated geometry manipulation later to, later stages of the project, so documentation, if we go to Revit, any other BIM platform, would it be fair to say that we've been kind of oscillating between the mesh and the NURB geometry the entire time, and you kind of try to stress that being able to go between the two is a very valuable ability. Would it be fair to say that for complex geometry manipulation, meshes with clean topology is kind of, would be your weapon of choice, and then later going to fabrication or documentation, you kind of start veering towards NURBs? Yes.
That would be more, actually, no, yeah, the answer to that is yes. You could arguably go as far as like midway through not 2D, 2DD, through DD with mesh-based workflows. But once you start getting into the more BIM-like environment, you're going to want to start finalizing your overall design to some degree, right? With changes that are somewhat much more high fidelity control, but also at the same time changes that are not as drastic, such as the sketching phases. So, once we get a series of NURB objects from this particular object you see on screen, and let's say we're like halfway through DD, we're going to start to look at Revit more in depth. We're going to start to look at BIM. We're going to start to look at drawings. And so all these kind of things require not meshes, but clean surface geometry, right? So we can start looking at how we can negotiate with BIM software. And that's, again, kind of, yes, to answer your question, that's kind of the intent, where we're sort of accelerating the first two phases of conceptual design and schematic design, and then looking at this design development as the phase where everything will pivot towards that BIM-friendly geometry, NURBs, for lack of better words. But I'm assuming that by then, this is case by case, but by then we have somewhat more control of a final geometry. And by final, I mean, the overall picture, not the small details. Cool. Okay. Well, if anyone else has no other questions, or like if you're, I don't know, if you're playing with the scripts and like nothing's working or something is working and it looks weird or it looks interesting, please feel free to shout out and let me know. But otherwise, we're gonna look at really quickly. We're gonna look at MetaHopper, which some people may or may not be aware of. And the reason why this is very useful is because, I'm gonna change this, is MetaHopper is essentially like how to organize the sort of script environment in a way that is not manual, because I'm sure as if you know, like creating Grasshopper scripts or creating all these kind of workflows can take a very long time to keep clean, organized, labeled, and for lack of a better word, it's just like easy for someone else to digest besides yourselves. So the point of this little plugin here, which is very useful, but of course you can also do this through the code, is essentially looking at object types. And when I say object types, I mean Grasshopper object types. So for example, here, there's a component that says get objects of the same type, and I'm going to plug in a panel. That particular panel is going to be read by this component, and it's going to return back a bunch of different objects. So Grasshopper kernel.special.jh panel, that is basically accessing the Grasshopper API and the classes. If you're familiar with that, then you're probably following along. If you're not, it's okay. It's essentially just accessing like the backend of Grasshopper and how what you see on the screen is constructed. And then there's a next little component that says set panel properties. So in this case, I can change this to be whatever, and then all the panels in the entire script will immediately update. Now that's super useful if you're cleaning up the script or color coding or just kind of doing some sort of organization for some purpose, right? Alternatively, you can also change groups. And this is just like the simple function of it, right? Like I'm just editing colors, but you know, what's really interesting is if you start looking at components and start extracting data from particular components. So if you have the plugin installed, there's object retrieval. So you can take a particular object. Say we take something like, say we take the panels, right? We want to see what the panels are connected to. So get connected objects is going to return back, oops, my bad. Is going to return back a panel that is connected to it. Let's do something like that. 1 second. I'm going to open up the example file that I've built, which is on the city end. Okay. So if we go down here, so if you open up the city file, I'm more interested in talking about like the MetaHopper aspect of it, like how you can collect geometries to be able to preview things and control things. So if you open up the file, you'll see that there's an arrow and something that says enable this component to create a fake sun simulation. But really the sort of intent of this is, let's say you built a series of scripts and you put a bunch of custom previews everywhere, right? So in this case, I'm getting all the objects that have that name. So custom preview, there's a bunch of custom previews floating around. Like there's one here, which controls sort of like the quote unquote roads. There's one that controls the next level of that, and one that controls lots that have been discarded, and anyway, so forth. There's a lot of previews, but essentially, if I can collect back all the custom previews, this little component is going to get back all those components. Now, once I have those components from the canvas, I can then extract information from that component. So I can do the component info, and then within that component info, I can extract things as inputs and outputs and things that are being used by said component. So in this case, what I want to know is what's getting inputted into the display components. So it's going to give me a rather ambiguous list of data, more Grasshopper kernel stuff. But essentially, all you really need to care about is the very last word, geometry and OGL shader. In other words, colors and the geometries. And it's a tree branch by component. So in this case, I want to get that particular piece of data and then extract what geometry is inside that kernel, right? So in this case, some of them are wrapped, so it's data wrappers. If you ever come across that, you can simply unwrap them using the built-in unwrap list component. And if you have a piece of data that is already unwrapped, it's okay. It's smart enough to sort of understand that. And if there's nothing in there, it'll disregard it. It'll discard it. But in this way, it's a way of communicating with your script without having to physically zoom in and out constantly and pan around. It's the intent of looking at how you can build a script seamlessly and then go back and extract the information you want effectively. So in this case, I'm extracting all of the B-reps and all the surfaces I created with the display components, and then I'm also doing the same for any particular color shader that was used within their display. So there's a bunch of display materials here that I'm using. So with that in mind, I can just quickly do something like this, where I can take the preview, and the color, let's get this. Nope. And then I can, if I turn on, let's say I turn off everything here. So nothing is on. Turn off. But if I just turn on this one single component after I've collected everything, everything will return back as expected. Like I said, this is very useful for sort of organization, and also if you're building a script that might be inherently messy and you just want to be able to share it with someone, but you want to specify like exactly what aspect of the script to share, like a particular series of outputs and inputs. You can do that using MetaHopper, right? You can search your own canvas and specify exact components and things that you need. And there's also things of operations where you can kind of toggle on and off remotely. So let's say we have a hide and show object preview. You can just toggle that to true and false, and then toggle this. So, update. There you go. You have to press on the update component to make sure everything actually processes. But once you update everything, you can enable all your objects or disable all your objects. And if you look around, you'll see that all the displays have now been disabled. And that's, again, working with, remotely in a way, working with Meta, Grasshopper, or MetaHopper, to be able to affect all sorts of different components. Now, this can go much deeper. Like what I'm showing is just a simple example of how to manipulate the canvas to your benefits and to your organizational conditions. But essentially, you can get groups by names, or you can isolate objects by types and whatnot. And then you can sort of do a series of batch processing. You can extract a series of objects that belong to a particular parameter or a particular component within Grasshopper. And then you can connect it back to human, which he made a funny little comment here, shameless self-promotion, but essentially the idea is like, you can play with different components, right? And have them mix and match for different reasons and make them out. So it's really useful. So, if I were to take, let's say, all these objects, and I press button, and just give it a big button, I'm basically reading all the display objects. And where's it at? Hold on. Take all my display objects. There you go. Okay, that works. So it's also a very effective way of getting data out of Grasshopper without having to physically hunt it down throughout your canvas sometimes. And this is also very, very useful if you're dealing with massive definitions, huge definitions that do many, many different things. Yeah, and as long as you sort of search your canvas correctly and you label things correctly in the proper way, then you can quickly and effectively create smarter ways of navigating your script and be able to share it with different people for different reasons and whatnot. And like I said, object attributes, so you can technically bake it with its proper colors and all that. But okay. So, any questions regarding that, MetaHopper or anything like that? The idea of being able to isolate a particular component and then having, changing different aspects of it globally. right? So all my sliders now have updated with the name. This is a slider. This is a slider, and it kind of travels across everywhere. Any questions, anything like that? Anything curiosity? Okay, so I'm not going to run through the city script particularly yet. I want to switch over to talking about how we can take organized scripts like these, or sort of after you build scripts in a particular fashion that's like easy to digest for other people and whatnot, how you can go one step further and actually share with people who don't even have Rhino and Grasshopper. So for the next hour or so, we're going to talk about, for the next hour, we're going to talk about Swarm, specifically speaking, cloud computing service that TT Core Studio has developed, and Sergey is the man to talk about that. And we're going to switch it over to him for a second, and he's going to go ahead and introduce Swarm and talk about how you can take something along the lines of, let's say this, or something along the lines of the other one, the Pavilion, and convert it to a Swarm app with sort of parameters that someone can use and edit and play with. Okay.
Cool. Hey guys. Okay, so let me share my screen.
Yeah, go for it. Do I have to stop sharing that?
Yeah, I think I have the power to override.
Nice.
Okay. Is that the right screen of 3? Okay. Let's hope that that is. All right. Can you guys see my screen? Yes.
Yeah, well, I can.
Okay, cool. Well, hi everybody. My name is Sergey. As Jonathan mentioned, I'm a developer at Core Studio. So I want to show you something called Swarm. So, you know, as TT being a big engineering firm, you know, we have kind of the most of the population of TT engineers are used to analysis platforms such as RAM, ETABS, SAP, or you know, some sort of sophisticated documentation tools. And I regret putting sophisticated in the sentence because I was about to mention Revit. But let's just say tools that take, you know, a large amount of effort and commitment to work with. Now, obviously, Grasshopper and Rhino are amazing environments for design. But you can't really expect to, you know, teach the entire, you know, 1,500 people that work for a firm like TT to be proficient enough to use those tools effectively. And we actually tried. We had kind of a campaign trying to promote the use of Grasshopper in the firm. But the reality is that in most offices, you'll have a very small population of kind of computationally minded people who are comfortable with those tools. And the problem always begins when you have some sort of an R&D or a computational group such as Core Studio, and when we have to, you know, build tools and then let other people use them effectively. And as many of you may know, Grasshopper scripts can be quite intimidating at times, especially when they get very complex and unruly. So this is why we came up with Swarm. So what you're looking at right now is the Swarm marketplace. And I urge you to go to swarm.thorntontomasetti.com to sign up. This is actually the important part. You will be able to view the marketplace as a guest without logging in, but you won't be able to do you know, most of the things that you would want to do, such as download and install the plugins and so forth. So please make an SSO account if you haven't already, and log in and enjoy. But the idea is that, you know, we have those, like each of those tiles is essentially an app, right? The same way you would get an app on your phone. I'm going to minimize this for a second. Okay. So, you know, here we have some sort of an app description, and we can install it in order to run it locally, or we can even run it in our online viewer. right? So for instance, here we have this blob that should appear any second. Okay. And we have a very clean UI that we can try and change. And so now I created a lot more segments in the U direction. So what's actually happening right now is we sent off the request to the web server, running an instance of Rhino using Rhino Compute. And now we got the geometry back. And as you can notice, I'm in kind of a Rhino agnostic environment, right? I'm just in the browser. I can do all this. If I want, I can download this as a 3DM file and continue working with it. I can save a state, which is something I'll talk about a little bit later. So I can interact with the geometry through the web browser, get the results back, export them out, and continue to use them in my design process. And what I'm using in the background is a grasshopper definition that someone else, in that case, Ben House, wrote for us. And I don't ever have to actually interact with that definition. I'm just setting the inputs that the author of the definition wants me to set, and I'm getting the results that I care about, kind of skipping all that complexity that's all hidden from me. Basically, what it's trying to accomplish is to cut the learning curve, right? I don't have to know Grasshopper, I don't have to know Rhino in order to use this. So how do we actually turn a Grasshopper definition into one of those apps, right? So in order for us to do that, we're gonna have to install a Swarm plugin for Rhino. So if you go to this dropdown over here that shows you your icon, and you go to downloads, so here you'll see the installer. It's just an MSI. If for some reason you're on your work machine and your IT department doesn't like MSIs, which is sort of understandable for security reasons, we also have just the zipped versions that you can try and install by yourself. So anyway, so what this is going to give you is it's going to give you a Rhino plugin, a Grasshopper plugin, which we'll also need to build an app, a Revit plugin, which I'll mention briefly, and an Illustrator plugin as well. So let's go back to our definition. And so here we have the same Pavilion file that John was showing you earlier. And let me see what's happening here. Okay. Trying to zoom selected. Okay, cool. So this is the Grasshopper definition that actually built it. And here we have the Swarm player on the right. So this is basically a way of running definitions in Rhino. And I'm just gonna show you really quickly. Like for instance, I can go to this app that I installed from the marketplace. And it's a bit of a heavy app, and also my laptop is struggling. So we'll get there in a minute. But essentially what this is once we see the UI. It's funny because I just got a new laptop and IT was asking me if I want one with a bigger graphics card. And I said, well, I don't do modeling work anymore. So now I'm regretting that decision. Anyway, so here again, we have this UI with lots of inputs, but again, I'm not seeing the monster definition that actually creates that tower, right? So I have inputs that I can play with and I have outputs that I can bake. So let's say here I want to, I don't know, increase the number of sides. So I'm gonna let's do 5, right? And maybe, I don't know, we'll do a little bit more vertical waves. As you can see, it doesn't live update right now. We do have a live update function, so I can click this button, and basically like a Grasshopper, every time I drag a slider, it will send a request to the server and get back the result. I tend to just kind of keep it simpler because, it takes time. for machines to communicate, and just to keep things a little smoother with large definitions, I just keep it off. So now I can click the run button, and we are sending the request. Struggling with the new laptop, and that's actually one of the benefits of Swarm, that if you have a machine that's not very gifted in terms of processing power, you can still compute monster definitions, because you're basically just setting some geometry and sending it off to get solved on a cloud by like an AWS cluster, right? So you don't have to worry about the limitations of your machine. Okay, so we got something, for better or for worse, and still finishing up rendering the output geometry. But okay, so this just got computed, and say that for whatever reason, let's blame it on the lack of taste. I like what I see, and I want to bake it into my document. So right now it's kind of a preview geometry, just like you would have with, a regular grasshopper definition. So now I can bake different elements. So here we got the floor plates. Now these are actual Rhino objects, glazing, edges, and you can also control what layers this is being baked out to, which kind of makes the organization part of all of this a little bit more streamlined. So okay, so this is kind of the general workflow with Swarm, right? We can get an app installed from the marketplace. We can use it here. But what do we do if we want to actually convert one of these scripts, one of the existing scripts, into a Swarm app? Well, you came to the right place. So first of all, one thing to understand about Swarm is that it runs on the cloud. So you kind of have to comply with the plugins that are installed on the cloud server. And that's a little bit more flexible than you might think, because, if there's a plugin that you really want, just shoot us an email, we'll install it. But basically in the documentation, we do provide a list of plugins that we support. And MetaHopper is not one of them, because it doesn't really make sense in the cloud environment. As John was explaining earlier, MetaHopper is really just a way of organizing your grasshopper definition, and it implies that you're actually looking at the definition in order to use MetaHopper. So I'm going to delete that particular section. The other thing that I'm going to delete are these preview components, because they don't do me any good, since, again, we're running this on the cloud. Grasshopper is not the one visualizing all of this geometry, so I'm just going to get rid of them. There was a time, once upon a time, when they were actually causing problems. I don't think that's still the case, but better safe than sorry. So okay, so we got rid of the previews. Perfect. So now what I'm going to do is I'm going to click on this plus button in the Swarm player, and this will take me to the editor. Here I can create a new app, and I'm going to call it something. So let's see, that's not how you spell AEC, AEC Tech, Pavilion 2020. You can add a description if you want. We can look at other ways to add a description. So okay, we have our definition here. So now what I'm going to do is I'm going to go to this Core Apps panel. And on the right-hand side, you see Swarm Authoring tab and Swarm Client. But what we're interested in here is Swarm Authoring. And the first thing that I'm going to do is I'm going to place the Swarm Builder component on the canvas. Now you notice that as soon as I did that, something happened on the right-hand side. So the Swarm editor, or the Swarm IDE, has a live link between the Grasshopper canvas and the IDE itself. So you can actually kind of have this, what you see is what you get experience as you're building your apps. And the second thing that I'm going to do is I'm going to right click on this component, and I'm going to turn off the debugger. As one of the developers on the project, I can safely say that I have Robert Oppenheimer level of regret of ever building out the debugger, just because it kind of makes things a little bit slower, because Grasshopper tries to render things, and Rhino has its own preview pipeline. The original idea was that you would also have Swarm kind of rendering things out for you, but there's really no need, and you'll have things going a lot smoother if you just don't have the debugger on. But anyway, so here we have inputs and outputs, right, in this component. So basically what we're going to do next is take inputs from the definition and plug them in, and you can see that now I have this UI element right here. Okay, so what do I do with this now? So first of all, I can rename this, and let's rename this as an input mesh, not particularly imaginative, but hopefully useful. And you can see that I just did this by right-clicking the component and changing the component nickname. If you have a well-structured Grasshopper definition, you know, somebody did their homework and actually went through and renamed all the components, and you know, there are some people who do that, which is great when you get a nicely laid out Grasshopper definition. We'll actually pick all of this up. So if you have, you know, either descriptions or if you have param names, this will all carry over here. Now, with regards to the descriptions, this is something we can also add. So this is, you know, a bit of a improvement in user experience. If we click this, we have just a regular description for, you know, a default description for the mesh param. I'm going to delete that, and I'm going to say base mesh for the Pavilion structure. And I really hope that this is how you spell the word Pavilion, and if that's not, I'm not from around here. Okay, so we have our inputs, and let's set some outputs. So first of all, we're just gonna do the mesh input, and then we'll add some bells and whistles on top of that later on. So okay, so what do we actually want to output, right? Well, we probably want to output, you know, the resulting mesh itself. So let me, well, let's see. So I guess, yeah, okay, so we want to output the panels, right? And I'm just going to do the same thing. So I'm going to create an output. We have now a bakeable component in our outputs list, which I can also rename and say output panels. Cool. So what else? Probably would be nice to get some sort of a thickness. I guess those are rivets, aren't they? Yeah, okay, cool. So we'll bake the rivets as well. So I'm going to hold the Shift key to add a second output here. Again, we have it updated in the UI. I'm going to call it rivets. And let's output something of a different geometry type, right? So we have surface, a surface here. So these are our surface panels. So let's call them that. And let's output some curves, and we'll be content with that for the time being. And I'm going to call this direction curves. Cool. So now we have the basic sort of swarm definition in the works, right? So what I can do now is I have this upload button that appeared here. I'm not going to bother adding descriptions to the outputs. You get the point. And when I click on it, it's going to ask me, would you like to create a default saved state for your app based on current inputs? And I'm going to say, nah, for the time being. And we'll get back to what those are. Okay, cool. So what I can do now is I'm just going to close Grasshopper. So we're just looking at Rhino and Swarm. And if I go to the app, now I can see when my laptop gets to it. Okay, cool. Now I can see the UI that we just built. And I can say, okay, so let's select the mesh. And I'm going to hit this plus button here. And you can see that it is showing me that there's one element there. The same color coding kind of works as with Grasshopper. Orange basically means empty, right? So I reference the geometry in, and I'm going to hit run. And this definition is going to take a second to solve. It's not the most straightforward definition ever built. And once it's actually solved, okay, so we're transmitting the results back, and we should be able to see the pavilion soon. And while this is happening, I might as well just hide our original geometry. Yeah, I should have really invested into that video card. Okay, well, while this is going, let me see if you guys have any questions. Because I saw something in the chat.
So for yeah. I think one question that I'm sure other people are curious about is like, you just mentioned it. The computation time of your definition, how does that reflect back on computation time for Swarm?
Yeah, so basically, you don't have to have a good laptop, but you do have to have a decent internet connection. We just went out on me a few moments ago. But yeah, so basically the computation time would be about the same in terms of actually solving the definition, right? Because, you know, Rhino is a single-threaded application. You're running it on the CPU. The CPUs on the cloud are not going to be drastically faster than on your laptop, right? So that's about the same. You do add a little bit in transmission time, right? Because I have to send the geometry up and I have to get it back. But you know, the trade-off here is that I don't have to have Rhino. I don't have to look at the Grasshopper definition. I can kind of, you know, just use this as an app, right? So Swarm is going to be a little bit slower, not as slow as you're seeing right now, because it's just, you know, my lucky day and everything works out great with live presentations as always. But yeah, I urge you to, you know, install Swarm, download some apps, and kind of see for yourself how snappy or not so snappy different apps are. And you will definitely run into some apps that, you know, will take a minute or so to solve, especially like solar radiation analysis or, you know, any ladybug related stuff. So, all right, so here what we have is basically an overlap between our original geometry and the geometry that came back from the server. As you can tell, once again, you know, this is just a preview, so we can't quite interact with it. But what I can do is I can go to this hamburger icon and disable shade solids and draw wireframes for my input geometry, and now I'm just looking at my output. Right. So, okay, well, this is pretty fun. So let's try to bake it, right? So I'm gonna try to bake the output panels, and now I actually have Rhino objects that I can continue to interact with and design with subsequently, right? So let's work a little bit more on our definition. So let's say I want to go back and yeah, so while it's loading. So here also in the panel, you can see that now I have one more item, which is basically my AEC Tech Pavilion. 2020 right here. Right now, this definition is private, so I can't, I'm the only person who can see it, but we can also share it with other people, and we'll get to that in a bit, right? So, okay, so let's open our definition back up, and let's click here and say edit. And the reason why I can do that is because I'm the admin, right? I'm the author. I have the power of life and death over this definition. So here I have two options, right? I can load app, I can use an open Grasshopper document. Now, load app is useful if you no longer have the Grasshopper file, right? Basically, when we submit a Swarm app, it gets uploaded to the server, and you can throw away your Grasshopper definition and forget about it ever existing. If that happened unintentionally, you can always recover it because we have it, right? So if you want to click load app, that would basically pull the definition from the server, open it in Grasshopper. You can edit it, do whatever you want with it, and push it back, and we'll update it for you. Otherwise, since I have the definition open, I just want to use an open document. Now, if you use the open document, there's one extra step you're going to have to do, is basically right-click on the builder component and say reconnect, just so that, you know, we reinstitute the UI and reinstate the UI, and then we have the communication going between the ID and the Grasshopper canvas again, right? And now you can see that here it says connected to Swarm, which is what you want to see. So okay, so let's add some bells and whistles, right? So how about controlling the gap between bands? Also, John, if you watch me pick something wrong, please let me know, because you're a lot more familiar with this definition.
So, okay. Gap is good. Gap is good.
Gap is good. Okay, great. Yeah. So I'm going to, hold Shift and add this to our input. And I'm also going to delete this group just in case. This is one of those things that I think we fixed it, but I just want to be safe. Because one of the ways we mark Swarm components is by creating this group around them. So I just want to make sure that that's the only group that's there. So okay, so now you can see that I plugged in the slider, and I have a slider appearing here. Let's rename this because it needs a descriptive name. So that would be a gap between bands, right? And it goes between 0.1 and 1,000. Let's do max at, I don't know, 100.
You're looking in inches, so think about realistic. So like think about like, I don't know, 20, maybe 24.
Okay.
Yeah.
What was it, 24? And in a second, that should have updated, but it didn't. So I'm just gonna disconnect it and reconnect it again. But in theory, that should all get synced up. So we'll be looking into that shortly. Okay, so we have the slider here, and let's add something else. So we have direction. Oh, this is the offset for the middle. Okay, let's grab that as well.
Yeah.
So we'll add this as an input as well, and just gonna delete that, and let's call it and offset distance. Cool. So I have some degree of freedom here. So if I want, I can just drag those outputs to kind of rearrange my UI. If I want my sliders to be on the top for some reason, I can do this with any components. I can rearrange this however I like. And okay, so this is looking good. So I'm going to update this. Still not going to create a saved state. We'll get to that soonish. Updated successfully. Gonna close Grasshopper. Go to the app. Cool. So here, once again, I'm going to reference the mesh. We see the preview. And now I'm going to say, okay, so let's do offset distance of 30. And the gap, let's do, yeah, I don't know. Let's just make it a little bit larger. Okay, so we're ready to roll. I'm gonna hit solve and send it to the server. Doing the solution, you can go get a coffee.
Okay, so while that runs, I guess, oh, it's actually processing a little faster. Okay, anyway, I was gonna ask, like, you know, running this on your local machine versus running this on a machine that doesn't even have Rhino, for example, the browser.
Yeah.
It'd be good to see like both examples.
Yes, exactly. So once we save a state, I'll be able to run it in the browser. Basically, maybe this is a good time to talk about saved states, but the geometry that passes through Swarm, when you find yourself in some sort of a design environment, right, being it Rhino or being it Revit, so we do have a Revit plugin, you have a way of actually inputting and referencing geometry from the document into Swarm. When you're on the web, we don't really have any tools for creating or authoring geometry. So instead, we use something called saved states. Basically, you can take the geometry inputs and outputs from a particular run and then save them as a state, right? So here, for instance, we got our geometry back. So we have, you know, we have one input, we have a bunch of panels in the output. So what we can do is I can go here and say save, and I'm gonna call it, I don't know, my saved state, and give it the description if I want to, but I'm not feeling it today particularly, and hit save. So this is gonna package all the geometry and send it to the cloud, which we'll see in a minute. Yeah, so this is basically a way of preserving that particular run, and we will be able to see it. Actually, I think I know what it is. I have like 6,000 rivets in there. Maybe that was a bad call. Okay, I'm gonna. This is the next. We have one more edit that we want to do to this app, so I'm gonna take the rivets out.
Would you? Yeah, I was gonna say, like, would you argue that computation time aside, visualization time also plays a factor?
Yeah, I mean, when you have a bunch of components, you know, running at the same time, you do have to render all of this to screen when it comes back from the server. So yeah, it definitely plays a role. In the web, maybe not as much because, well, actually, I shouldn't say that. It still plays a role. It's just there's different kind of preview pipeline that is in play here. So, okay, we're getting there. Cool. So current state saved. So what I can do now actually is if we go to the browser and I go to so this is we're back at the marketplace. So if I go to my apps, so these are apps that so let's do apps that I authored, and somewhere in here. Okay, so here's our app, right? Again, it's private to me for the time being. We can't run it in the browser quite yet, but in the saved states, we do have my saved state right here. And this is great because what I can do is I can click on it and do several things with it, right? So first of all, I can share it with other people, right? So for instance, you know, say we're working with an architect or some sort of a client, right? And say TT engineers created a grasshopper definition that turned into a swarm app that configures a truss or a bridge in a particular way, right? And then you can make an app out of it, send it to the client, and the client now has the ability to actually play with the inputs and get different configurations and kind of see what you know, what works for them, what they like. And saved states is a way of kind of benchmarking the configurations that they prefer. And now I can, you know, type in an email, say John's email, and share it with him and say, hey, you know, I really like this. Let's move forward with this. I can also just use it for my own use, and we'll see it in a second. You know, just to benchmark things that I like and load them later in the process. But right now I'm just going to click make default, and you can see that now the run app and browser button is on. So I'm going to click on that, and now we're taken to the browser. We can see the menu here, and what's happening right now is we're loading that definition and the 6,000 rivets to be displayed. And then we'll be able to interact with it online as well. So actually, I'm just gonna let's do this edit right away, just hopefully to make things a little smoother. So while this is loading, let's fix our mistake here, and we'll do a couple more things. So okay, I'm gonna hit edit once again. So this is gonna ask me okay, this is still going. Okay, so I'm going to use an open GH document, and we'll do the same reconnect thing. So it's trying to connect and read that geometry. Let's try to do it again. Okay, it says unable to connect. So in that case, okay, let's actually, maybe this is a good point to show loading the definition from the web. So here I'm going to go ahead and click. I'm just going to wait for it to finish updating. And okay, so I'm going to edit. Okay, and load app, right? So now this is pulling the definition from the server, and you'll see that my name has changed, not my name, but the definition name has changed this, you know, this weird GUID. This is kind of how we store it in the server environment. And now it opened the definition here, and now we get this UI back. Perfect. So okay, let's get rid of those notorious rivets. So I'm just going to go ahead and disconnect it from Swarm, disconnect it from the output. So we have, okay, so when this happens, we also have something called hard sync. So let me demonstrate that. Basically what hard sync is going to do, it's going to read all the parameters in the definition and update them, sync them in the UI, which, okay. Let's try this one more time. So okay, I'm actually going to just create a new app and hard sync it this way. All right. So we can reconnect. Cool. And now we can hard sync. Okay, so that's something for us to fix in the next release. All right. So let's, while this is loading, let's go back here and see how our browser is doing. And okay, so the browser loaded all of this. And now again, you know, we can see our panels. Right now, we don't have any attributes assigned, so we can't really, there's nothing to visualize by. We can visualize by layer, so at least we have different layers. And we can also control visibility of different items, right? So we can select this, and yeah, we can hide the input mesh, and just have our pavilion right here, right? So okay, so let's. I'm just gonna close out of all of that. Nope. Nope. Okay, and we're going to edit it once again. Load it from the server. And in a second, we'll be able to proceed with making the edits to the app. In the meantime, if you guys have any questions, please do let me know. Okay, so let's try this again. Okay. All right, I guess the rivets are staying with us. All right, so this is something for us to fix. Anyway, so let's try and add some other things that were a part of the original definition, right? So for instance, let's try to add attributes. Attributes are an important part of working with Swarm because what they allow you to do is they allow you to use the visualization options in, you know, Spectacles is our online viewer that you see in the web app. So, oh, now it actually did what I wanted to do. Okay, perfect. So let's try and, okay. Okay, I think Raina is trying to fight with us on this one a little bit. Okay, so let's return the color back, right? So here we have this gradient that was originally coloring our panels. So what we can do is we can go ahead to the constructor and say construct attributes. And once we have this here, oh, this laptop is really struggling. Okay. So now I can, okay. So now I can connect the color to the color input of the attribute component. And you know what, let's update it as is, and I'm gonna restart Rhino because something is, yeah, it's not collaborating. So I'm just gonna, okay. So let's update this as is, no save state for us. And so I'm just gonna close and reopen Rhino because something is funky. Okay, no changes to the pavilion. All right. So presumably, so another good thing about Swarm is that, as a repository for your Grasshopper definitions, if something goes really, really terribly wrong and it crashes, or you don't really lose your work, because once you commit the definition to the online storage, it's there, and you can access it from any machine, from a browser, from a series of different plugins. So in a moment, we should be back on track.
I guess while you wait for this to open, you could quickly touch up on the idea of sharing, because I know you mentioned sharing via email, but there's also making something completely public versus enterprise public and so forth.
Yeah, exactly. So this is something that we'll get to in a moment, because once we actually put together our app, we'll be able to do stuff like change its icon and add its description. And also, yes, as John just mentioned, we have different degrees of publicity, let's call it this way. So you are able to share an app with an individual person. You're able to share an app within your domain. So say I registered for Swarm with my @thorntontomasetti.com account, and I want to build an app only for TT, right? So here, in the menu, we'll see in a second. Yeah, so here I have the marketplace, and then right underneath the marketplace I have the Thornton Tomasetti section, right? So if I click on that, once the web app loads, yeah, so here are the apps that are only visible for people with an @tt.com email, right? Or I can make it completely public, and I can just put it out on the public marketplace, and then everybody can use it. You can see that there are like these tags that say free, and potentially some of them that have a price on them. This is not something that has been implemented yet. We're not taking anybody's credit card. We're not charging anybody, but this was part of the idea that a marketplace could be some sort of a platform for users to also capitalize on their IP. So if somebody wants, the same way as you have free Android apps or iOS apps, you have paid iOS apps. So basically implementing the same concept for architects, designers, and so on and so forth. Okay, cool. So let's go back to Rhino, and can open Grasshopper. And yeah, we'll be, hopefully without the rivets, we'll be able to run things a little.
Yeah, I mean, maybe you just disable that whole group, the rivet group, just like disable it to decrease computation time.
Yeah, let's do exactly that. And hopefully we'll be able to see this solving live as well. Cool. Okay, so let's edit it once again. I'm going to load the app from the server. And once the definition is pulled down, we'll be able to continue editing it. All right. This will hopefully take no time at all. Okay, cool. So we're back on track. All right, so here again we have the UI. The first thing I'm going to do, okay. So you're saying disable just everything here, basically. You're muted.
Sorry, I meant delete that group, and you should be good.
Just delete that entirely. Okay, cool.
Cool.
And I'm going to set the debugger to off. Okay. So now let's add some color, right? So here we have the attributes component. We can feed the color to it. We can feed a lot of different other attributes, basically as a key value pairs. I mean, maybe let's do it now. Famous last words. So mesh area, we'll just calculate a mesh area of each panel. And I'm going to create a key called mesh area. All right. And so let's just check the tree structure really quick. So, okay, they should be matching. So we feed the values, we feed our key. So we have the same number of attributes as we have the actual geometry. So what I'm going to do now is I'm going to disconnect this from the output. And I'm going to create this inject component. So basically what we're doing here is we're taking the geometry that we just computed and we're injecting the attributes into it. And you got to watch out for the trees so that you don't, graft things out of control. And I'm going to duplicate this mesh param, because one important thing is you won't be able to connect just any component to the input or the output section of the builder component, mostly because we only support params, right? So it always has to go through some sort of a param. And a param in Grasshopper is basically just a container, right? It's a placeholder for geometry or data of a particular type. Okay, so I'm going to take that and feed that to outputs. And our name was saved there. So hopefully, yeah, it's still called output panels right here. Okay, perfect. So now we have the values, the color, the output panels. We don't have the rivets. And we'll just roll with that. So I'm going to update that. Still going to say no to the default saved state. And we're going to create a new one since we just updated the app. So I'm going to go there and we'll be able to run it. So now it's actually, it just committed the app and it's trying to load the UI back. And I have a second instance of Rhino open, which we don't want. So let me quickly close that. All right, so here we have our updated UI. I'm going to close this and we're going to input this as a mesh and we're going to run this and hopefully the gods of AWS will be easier on us this time. Okay, so we already solved the definition and we're rendering the output geometry back. Okay, it was the 6,000 rivets. All right, so let me hide this and let me also hide the wireframes. So yeah, so now we have, you can see that if I also hide the surface, the underlying surface and its edges, that now we have the colors that were assigned in Grasshopper. And if we bake this, we'll also be able to see this. So the nice things about it is that now we can create, toggle the live mode back on, and we can start playing with it. So kind of like in Grasshopper, every time we move the slider, geometry updates a lot faster. Cool. And let's once that's done, let's decrease the gap a little bit. So again, live update, sending geometry to the server. Great. So let's update our saved state so that we actually have some color on the web. So, right, once it's finished solving this last batch, we'll be able to do that. Unless it's already done, it's just doing funny things. All right. So I'm going to hit save. No, it's actually okay. So let's exit out of that and let it render the geometry properly. Okay, cool. So I'm going to turn this off, and I'm going to go here and hit save. And this is going to be my new default saved state. And I urge you to use actual names for things. Okay, so save that. So now what we can do, if we go back to the web app, and here we can see, okay, my apps. Cool. And let's search for it. So this is, okay, is that our, oh yeah, I now created the second app, okay, cool. So okay, so now if we go to the web browser, hopefully, again, this is gonna be a lot snappier this time. Which is still, we're transferring meshes over the web and rendering them in the UI. But once the geometry comes back, we'll actually be able to also look at the attributes, right? And that actually, let me show this to you in Rhino. So if I bake those panels, hopefully, and that might have some additional setup needed, but in the properties tab, yeah, so now we have the mesh area here that's been calculated for this panel. And this is, something we can use. It's already baked into the geometry. This is something we can use further in our workflow. Okay, right, because we didn't update the saved state. All right, so let's do this now. So we're loading the rivets. So let's go back to the app and let's go back to the saved states. And here we have another state that I'm gonna make default. Go back to the app, and now this is gonna be, yeah, a lot faster. Okay, cool. So I'm gonna disable the input preview again. And what I can do now, so one of the great things about the Spectacles viewer on the web is that we can actually color things by certain properties. So here I have the mesh area attribute, and I can actually see the areas, the attribute that we just assigned in Grasshopper. I can visualize it very clearly in the web browser. So this is just a nice way of kind of taking a look at geometry and the attributes that come with it. Okay, great. So now let's do a couple more things. So let's say we want to publish this app, right? So I'm gonna go to the app settings, and in my apps, so right now it's private, so I'm the only one who can see it. So let's, okay, I see Tech Pavilion. And I'm going to click Edit App. So this is kind of where we can add the description. I can make it public or domain only, so I'm going to make it public. Yes, make it public. We can change the icon. So for instance, I screenshotted this pavilion a little bit earlier, so we can use this as our icon. And then I can kind of set what platforms it's supported in. So Revit, CSI, Illustrator. this is kind of on me as an author. Theoretically, any Swarm app can run on any platform. The question is, how meaningful is the output? So for instance, if you have a mesh with no attributes, you will be able to bake it into Revit, but it's not going to be a BIM element. It's just going to be a shape, right? So this is on the author to define where this app is intended to be used. I can add more people as editors or admins, and I can also allow the Grasshopper file to be downloaded. So this is a way of kind of making your project open source in a sense, right? So people can download your Grasshopper file and fork it, make their own apps with it, and so forth. So I'm gonna save the changes, reload the page, and yeah, now we have our app. And if we go to the marketplace, then we'll be able to search for it here. Yeah, so now it's public, and you can find it as well.
Not to cut you off, sorry, but we have a couple minutes left before we hit 12, and I want to keep on schedule so that way people have other things to tend to. This workshop was set up for 9 to 12. And if you have somewhere else you need to go or another workshop you want to get ready for, please do so. But before everyone leaves, Sergey, please do some closing remarks, and I will also do some closing remarks. So go ahead.
Sure. So one of the things that we do want to announce, and we made an announcement earlier last month, I suppose, that we are merging with Shapediver. I think it's important to mention that. So Shapediver is basically a similar online platform, mostly targeted for online configurators. These guys are pretty amazing, so I'm just going to quickly show them. And yeah, they're also using cloud compute technologies, so we're merging into one entity, and soon, at some point, we'll be releasing kind of a new iteration of all the plugins and the web app using our merge technology, and hopefully with a lot less quirks in there. But yeah, so look forward to that. Please mess around with Swarm. You have all the downloads. If you haven't made an account, please make one. And if you have any questions, you can always reach to us on Slack or via any of the numerous ways of communication that exist out there.
Yeah, to follow on that, thank you so much for attending the workshop. If you've been following along and messing around with the files, great. If you've just been kind of watching and learning, if that was a method, that's also awesome, regardless of what you chose to do. Thanks again for attending. Thanks again for being a part of it. I hope you guys have a great rest of the symposium. Just enjoy everything that's going on. And also, like Sergey is saying, I know we have a lot of ways to communicate: Slack, the chat, Link Central, email, etc. As long as you have a question and you want something to reach out, please do. We'll be around for the weekend and the week coming, and the Slack channels are open. We will respond, especially now because we're working on this actively. Whether it's Grasshopper, Rhino related, Swarm related, or hackathon related, doesn't matter. Reach out. Thank you so much for paying attention, and let us know if you have any feedback. And if you made something cool, post it. We would love to see all you guys' stuff. This workshop, other workshops, doesn't matter. But yeah, thank you so much, and hopefully we'll talk soon.